Okay, so this lesson is about concavity. So first up, let's look at some definitions. So the word concave is whenever a graph curves upwards. In physics, they probably define that as when something curves inwards. And then the opposite of concave is convex. Convex is whenever a graph curves downwards. Or in physics, they would have said that convex is whenever something curves outwards. If you see concave down, it just means convex. So those two terms are used interchangeably. So the AP wants you to understand three distinct things. The first one here, it says that the graph of a function is concave up or down on an open interval if the function's derivative is increasing or decreasing on that interval. So if you're looking at the derivative of a function and the derivative is increasing, that means it's concave up. And if you're looking at the derivative of the function and the derivative is decreasing, that means it's concave down. The second standard is the second derivative of a function provides information about the function and its graph, including intervals of upward and downward concavity. So this is basically saying that if you want to find information about concavity of something, you could look directly at the second derivative. And then finally, the third standard, the second derivative of a function may be used to locate points of inflection for the graph of the original function. So there's a term there that we haven't talked about yet, points of inflection. A point of inflection, or you could write POI for short. A point of inflection is a point where the graph changes from concave to convex, or it could change from convex to concave. So now let's examine a graph and see if we can figure out where on this graph is the function concave versus convex. So we said that concave is whenever your graph curves upwards. So if you look at this blue part of the graph is curving upwards in that interval of -2 to +2. So you can think of this as being a bowl. If you were to pour water on top of this, on top of the graph right here, this bowl would fill up with water. So if you can pour water on a graph and it pulls up like this, that means that it is concave. So the opposite of the concave is convex. Convex is whenever your graph curves downwards. So if I pour water on the graph right here, the water is not going to collect in that area. It's just going to run off. So this interval right here on the left, this is when the graph is concave. And it looks like that interval would go from -2 all the way up until +2. And then this other part of the graph, the green part, where it curves downwards, this is where it is convex. And that interval looks like it'd be between +2 and +6. So right here in the middle, where it changes from being concave to convex, that is our point of inflection. So the interval that is concave looks like it's between -2 and +2. And the interval whenever it's convex looks like it goes between +2 and +6. And then the point of inflection, we just need a single point in space. So that point looks like it's right at 2, 0. So here's another graph. So this is the graph of y is equal to x squared. So we only are looking at a part of the graph, but we know that this graph goes on forever up and to the left, and then also goes on forever up and to the right. And the further up it goes, the steeper the curve is. Just by looking at the graph, it looks like everything we see here is concave upwards. So if I were to pour water over the top of this, that water would just pull up inside of it. So we can say that this graph is concave. And we could actually assume that this is going to be concave everywhere. So as we go off to the graph to the left, it's going to continue to get steeper and steeper, so there would not be any point of inflection to the left. And as we go off the graph to the right, we can also assume that it just gets steeper and steeper. So our interval for when this is concave would be negative infinity to positive infinity. Or we could just write that as all real numbers. And since it doesn't look like this graph is convex anywhere, you could just write the symbol for the empty set. Same for the point of inflection. Since the graph never changes from concave to convex, that means that there is no point of inflection. So have a look at this graph and try to figure out if you can see where this is concave, where it is convex, and then just estimate where you think the point of inflection will be. All right, so let's think about concave first. So this is curving upwards over here in this area. This graph goes on forever up and right, and it's going to go on forever down and left. So as it leaves the graph, I'm going to assume that the concavity does not change. So this graph is concave in this area right here. For sure, if I poured water down in this area, that water would just pull up right here. But at some point, that changes. Over here, it's definitely convex to the left. So at some point between this convex area and this concave area, there has to be a point of inflection. So that point of inflection has got to be in here somewhere. And if you zoom in to this, you can sort of see, so this is curving downwards, and at some point it's not curving up or down, and then it starts curving upwards. So I'm just going to estimate that the point of inflection is somewhere halfway between this height and this height. So I'm just going to say it's like right in here. So I'm going to say right there is my point of inflection. So that point would be, let's say that's x is equal to 4, and the y value, let's say negative 125. So my interval for concave, the interval would start at the point of inflection, and the x value of that was 4. And we can assume that as the graph goes off the chart to the right, that it's going to continue to be concave. So that would be until infinity. So my interval for concave would be 4, infinity. Using that point of inflection of 4, I would say that it stops being convex at 4. And as you go off the chart down to the left, we can assume that the graph continues to be convex forever. So it would be negative infinity. And then the point of inflection would be 4, negative 125. So the last thing we'll look at today is how to find concavity analytically. So this is a way that you can find the exact intervals and the exact point of inflection. So in order to do this, we are going to look at the second derivative of a function. If your second derivative is positive, that means that the function is concave. So we talked about convex being the opposite of concave. And what's the opposite of something being positive? Well, something being negative. So if f double prime of x is negative, then that means that f of x is convex. So these are opposites over here, these are opposites over here. And finally, if f double prime of x is equal to 0 itself, or if it does not exist, that means that f of x could have a point of inflection. Just because the second derivative is equal to 0 or does not exist doesn't mean that there's definitely a point of inflection there. It only means that there could be one there. In order to find out for sure, you'll want to do a sign test.